Okay, so now we go ahead and explore the exception entry, return, and the SysTick timer. So what the screen that I'm on right now is our code spaces, and in the code spaces, what I want you to do is go to the README file, and at the very bottom, I added this new documentation for the M3 class of devices, right? So it's a generic user guide, so it lists everything that you should know about the M3 controllers. So if you're working on, let's say, M0, M33, M55, simply look up this entire string, which is Cortex-M, your processor's number, device's generic user guide, and you should find a documentation corresponding to that specific M device or M CPU. In our case, we're going to use the Cortex-M3, hence I've linked this. Now, if you don't have this, what you would need to do is do git pull minus minus rebase. If you execute that, you'll get the README file will be updated. Um, and the last URL here is what you're seeking. Also, if this doesn't work for you, no problem. Go to the GitHub repository for this course, which is at this github.com/inpyjama slash hyphen m hyphen assembly, and you can just go to that URL. And once you're at that URL, just scroll down, and then this is the link for us, right? And the reason this documentation is important is because we will have the exception entry exit and the SysTick timer related information in this document. So let me go ahead and click this, and it opens this web page based documentation from ARM. So this is ARM standard documentation. You can also go to this download section here, click, and then download the PDF version of this. I'm going to stick with the web version. That's good enough for us. And let me also get rid of um, the toolbar. All right, so this is the documentation. Then what does this do? Oh, it lightens things up. Nice. Okay, so what we're looking for is within the ARM Cortex M3 processor, we are looking for exception model, and then from within that, we are looking at exception entry and return. And why are we looking at this specific thing? Because recall, I told T1 is executing, an interrupt happens here. In this case, the SysTick interrupt. That's why we are interested in SysTick timer. Once that interrupt happens, it jumps to SysTick handler, the interrupt service subroutine, the ISR, so to speak. And then within that, we said it will be using the S1 stack corresponding to task 1 stack. And this we call the exception entry, right? And when it's done executing the ISR, we said that it will exit out of the exception, and the exit will happen to T2. That we said was the trick, right? Getting CPU to execute the scheduler is because of the SysTick. That's how we achieve it. Now what I want to show you is what happens during the exception entry and exit. That gives us an idea of what all CPU registers the CPU will automatically save on the stack for us, and what are the CPU registers we will need to save. And the save and the restore that we are going to do from the ISR for SysTick. All of this gets clear once we start to implement things, so don't sweat, just follow along. So I'm within the exception entry and return. You can read all of this. The summary is this, right? So what they're talking about here is, let's say the stack pointer, okay, I need to change colors. Let's see if I can manage to change that. Uh, I can't. So what I'm going to do then is turn the lights off. Nice. Okay, let's come back here. You can read this page. and it'll give you a lot more details. What I'm going to do is, so we were having a stack where we said, hey, it's at pointing at the bottom of the memory and it increases upwards. What these people have done is flipped it, right? So their stack pointer is here and it goes down, so to speak. They have inverted the memory. We were going from, let's say, 0 to 10. They're going from 10 to 0. So this way is same as this way. Difference in imagination, but it kind of, does our job. Okay, so the stack pointer initially is pointing here. When an exception happens, the CPU automatically will fill these many words, so to speak, and word is 4 bytes, right? So in memory, it is going, you can see that the difference here is 4, which means each of these is 4 bytes away, right? So what it is going to do is save the CPU registers like so, right? So it is going to save the status, program status register, which is kind of giving us the information about what this CPU was doing in terms of calculations. Was a negative number generated, was a 0 generated, so on and so forth. So it's going to save that information here. The next register it saves is the program counter. Hey, which instruction was I executing when this interrupt happened? Or which instruction was I going to execute when this interrupt happened? So it will save that information here. Then it saves the link register, which is R13, I suppose. And then it saves the R12 and it saves R3, R2, R1, and R0. Notice that it's not saving R11 through R4. So something's going on there, right? The CPU automatically doesn't save those registers for us. And what we are supposed to do is save those manually. And save where? Well, where all are these stored? On the stack. So what we are then supposed to do is use the push and pop stack instructions to push these on the stack, so push them here, R11 through R4. And why are we wanting to do that? Because the complete context of what the CPU was doing is a sum of these registers that the CPU automatically saves for us and the one that it has not saved. So we want to ensure that the CPU is completely clean before we start to fiddle. Well, it's completely clean in the sense everything that the CPU had within it in terms of register values, the programmer's models, the registers in the programmer's model, we want to get those out and park them, save them, so that we can continue to use the registers of the CPU, do intermediate calculations, all of that. So that is why it is important to save the registers that are not automatically saved. Again, when the interrupt happens, the CPU saves all of these registers on the current stack automatically, whichever stack it was using, whichever SP value it was using. And then it will go ahead and change the program counter value to the interrupt subroutine's address. That's what it does. And we talked about this in the exception model. The key point is some registers are not saved. And those registers we are supposed to manually save as soon as we land in the ISR. So, something like so. We're supposed to do something of that nature, right? Push the registers onto the stack. Hopefully, you're now getting the idea of how the context of the CPU is saved. The CPU does it for us. These registers, it will save automatically. And then we are supposed to use the push operation, the push assembly instruction, to push the unsaved registers on the stack. Now, once we have done that, once we have saved everything from the interrupt subroutine, we are free to change the stack pointer register to point to S2. So at that point, we were executing, let's say T, okay, let me pull the whiteboard. So we were saving the T, or we were executing T1, interrupt happened, As soon as the interrupt happened, some 8 registers went on to S1 already. R11 through R4 did not go there. So we kind of push them here. Once that happens, we have saved everything relating to T1 onto the stack. And now what we are going to do is change the stack to point to S2. And on S2, we have 8 plus 8, well, this R11 to R4. Those registers we have already kind of saved there, in the sense we have either manually configured this region to become the right CPU context, or this was saved when something of the nature, okay, this needs to go. How will that go? Yes. When we were doing T1, T2, T3, back to T1, and then back to T2. So either T2 was executing for the first time, or it was executing for the second and third, fourth, fifth time. If it was executing for the first time, this was the manually crafted CPU context. If it was executing for the second or third time, it was the one that it saved from here. If this is not clear, go back, listen to my words very carefully. But the idea is, if we change the stack pointer to S2 now, this is S2, what is going to happen is, as the CPU exits, it's going to, well, first off, before it exits, we are going to pop these registers, which the CPU automatically doesn't do. So R11 through R4 gets loaded by us from a different stack, the S2 stack. And then we just say, hey, return from the interrupt. And as it does that, it will automatically restore these 8 registers into the CPU. And these are the ones that correspond to the context of T2. And if this much is clear, slowly it will kind of sink in you this idea of how an external ISR can be used along with the knowledge of the programmer's model to trick the CPU into executing multiple processes, right? Okay, so let's then go back. So this is what I wanted you to know about the exception entry. And the idea is that as the CPU, as the exception return happens, so this kind of details a little bit about what the LR value needs to be and so on and so forth. We wouldn't bother about that, but the CPU does some job for us of saving and restoring, and the idea is save to S1, restore from S2. That's it. Okay. This will sink in, trust me. As we go on to writing the code, things will fall apart, everything will make sense. Now let's move on to talking about the SysTick timer. So we go to the Cortex-M3 peripherals. So this CPU, turns out the M-class CPU, so this is the actual CPU, then it has got the SysTick, and it has got the NVIC as peripherals. So it has got these two as peripherals, and what we are going to do, this is the interrupt line essentially. So what we are going to do is we are going to use the SysTick, we're going to program it to fire periodically, and as it fires, we get the ISR. ISR is where we do the scheduling from. So we need to know how to program SysTick, or what it is, and how to go about programming it. Right. So we are going to look here at the system timer SysTick. And what it says is, it talks about it being like a 24-bit system timer. It kind of, counts down to 0 and it reloads and then wraps around. But then every time it hits 0, it can raise an interrupt, and that's what we want. So now you can also imagine the time between task switches can be controlled by loading the appropriate value of the SysTick timer. You can have things context switch very fast, or you can have them context switch slowly depending on the timer value, right? And then these are kind of the registers we'll program. These are the addresses of the register. These are super useful. So we are going to program these. And all of these needs to be programmed from the privilege level. That is what we'll start off in. So our reset handler will be in privileged mode. So that's not a problem. These are the 4 registers. One is for control and status. One is to reload the value. One is the current value, and then the calibration. So we'll kind of just, let's just touch upon. So we have the control register, which is having like a count flag, then the clock source, tick, I think it is the tick interrupt or tick, let's see, what is tick int? Yes, enable the SysTick exception request. So this definitely has to be set to 1 so that the interrupt is raised to the CPU. Counting down to 0 asserts the SysTick exception request. Software can use count flag to determine if SysTick has ever counted to 0. We wouldn't care about the count flag, but definitely tick int and enable. These are the 2. And then apart from that, we are going to also program the reload value register. And this is the 24-bit value that we get to load into the timer. And from that value, it will count down to 0, right? Value load into the CVR register when the counter is enabled and when it reaches 0. All right. Then the current value register, we don't really care about that. Calibration, not as much. And then there are some tips to how to go about using SysTick. All right, so with this then, we pretty much now know how the exception entry and exception is to be used. And we also know something about the SysTick timer. And next what we do is go ahead and actually program it. One other thing that I want to go to is the vector table. And in this vector table, somewhere we have the SysTick, right? So the SysTick is the 15th interrupt or the exception. So this is how things are going to look then. So just a moment. Yeah, okay, perfect. Right. So we have the CP, and this is again me stitching together so far what we have learned. It's too much theory so far, but it's just necessary. So we have CPU, it has nice resistors, then it has the XPSR, there's PC somewhere here, right? Now what we have is we have the SysTick, right? SysTick, and what we said was we will have T1, T2, T3, corresponding there will be S1, S2, S3 as the stacks, and we are going to start off in the reset handler. So as part of the reset handler, what we are going to do is program the SysTick. We are also going to have a global variable somewhere that remembers where is S1, where is S2, and where is S3. Right, so S1, S2, S3, and let me go ahead and put a star, which essentially means, hey, the current free location in these stack areas. And this will become clear. Again, why this specific thing? As we implement, things will become clear. And we're going to have this, so to speak, a circular linked list here. So we need to have that. And one more important thing, we need to have the SysTick handler, right? Which then means our vector table, and I'm going to erase all of this, which means our vector table now will have the SP, the reset handler, and then at the 15th location, there would be SysTick handler. So we need these three entries in our vector table at least. Then we need 3 stacks. We need 3 functions, T1, T2, T3, and we need, so to speak, a fixed linked list, a circular linked list that the scheduler can use to hop between Where was the last S1, last S2, last S3? If so far you've been on board with the picture that I drew, you're all good. And trust me, as we start to write code, everything will make sense. We'll manually do the scheduling, and it will be fun. Yeah, if there are a few things that are kind of still, you're not convinced with, hang in there. As we do the experiments, my gut feeling is things will become super clear. So just trust me, ride along, and then see the magic happen. With this, I'll catch you in the next one.